So welcome to our last morning of the bootcamp week. We're pleased to have Fanny Yang joining us from ETH Zurich. So Fanny was a PhD student here at Berkeley and a postdoc at Stanford. And this was supposed to be sort of a homecoming as a long-term visitor, but she's having visa problems. Her research is on theoretical aspects of machine learning. And most recently, that's been in the form of overparameterization, overfitting, and adversarial examples for deep learning. So today she'll be talking about reconsidering overfitting in the age of overparameterized models. So Fanny, take it away.
Thanks a lot, Pauline, for the introduction. And thanks for being there early in the morning, despite it being a remote talk. Thanks for the organizers to invite me and accommodate this difficult situation with the non-arriving visa. So yeah, today I wanted to give a talk that's somewhat a modified version of the tutorial we gave at NURBS with Spencer, Vidya, and Daniel. And with the difference that it should be a bit more interactive, so please interrupt me at any time. The Matusa and Pauline have mics; they can walk around and yeah, so I can hear your questions. Okay, so we'll start a bit in the spirit of this workshop and also what other talks have talked about, and start with the textbook wisdom of generalization, overfitting that everybody is familiar with, and then go over to the overparameterized setting. So the supervised learning problem is to learn essentially a function, or some true function, let's say in this case, the red function for a very simple 1D problem, using samples that are noisy from this function, which means you have xi, and let's say 20 samples of xi, and for each xi you have a noisy version yi of f star of xi. Now, what you could do is you restrict yourself to search in a function space of polynomials of degree 2, and then fit this function to fit the random samples the best, like these black crosses. If you choose a polynomial of degree 2, you will not get very close to the true function, even though you are avoiding noise. You cannot express this cosine function essentially with this polynomial of degree 2, so you'll have high statistical bias. But on the other hand, a good property of that is that you don't have large variances. If you sample many times these 20 samples, you'll see a function that kind of looks pretty similar each time. So we have a problem of underfitting if we choose a model that's too simple, and if we have a model that is too complex, such as in this case, where we can interpolate the data, we can interpolate all these crosses, then we'll have the opposite problem of having a very flexible function class where we can express our function of interest. So we have a small bias, but we will have a lot of fluctuations and hence a high variance. Every time we pick a different 20 samples, we'll see a very different function that is fit. Okay, so the blue function is very different than the true one, the red one. Okay, so as also Nati has talked about and many others, I mean, the idea is to find the right model complexity so that we are optimizing this bias variance trade-off. So instead of picking a very complex or very simple model, we pick something in between that can either be, in the case of polynomials, just choosing a function class that is a bit restricted, but not too much, or we can use a very complex function class like the polynomial of high degree and use some regularization. Okay, so in both cases, we can end up with a pretty good estimate prediction model f hat that's close to the f star. This is classical theory. And what classical theory has not tried to answer is the case, what if we increase this polynomial degree even further? So with polynomial of degree 20, we can fit 20 samples perfectly. The question that has not been asked is, what happens if we increase the polynomial degree past 20? And we don't regularize, so we still allow it to fit. Okay. So why do we now ask this question, and why has this become a question that got a lot of attention in the recent years? So that has to do with the phenomenon called double descent that we observed on neural networks, we meaning the community. And so what is this phenomenon? I just want to go through it a bit more slowly because there are actually quite a few things happening when we look at the empirical data. So here we see the classification accuracy on a C410, where we train with 15% added label noise. That's classification now, not regression. And what we want to look at is the test error as a function of the width of the complexity of the neural network. In this case, it's just the width parameter of ResNet 18. So these are experiments from OpenAI like 4 years ago. And so basically, as we traverse the x-axis, we're increasing model complexity. So that's kind of a way to look at it. And by just having more and more parameters. So that's just one way to look at what width is. Essentially, we increase parameterization, overparameterization, we go further to the right. Okay, so in the underparameterized regime, what we see here as the solid line is the test error, and the dotted line or the dashed line is the training error. And the underparameterized regime, we actually see something similar like the bias variance U curve. Due to the bias variance trade-off, we see this U curve of the test error, while the training error decreases since we have more and more flexibility to fit the data. So that's what we know. This is basically this textbook wisdom. And the question is, once we hit a complexity that is big enough or expressive enough, a model that's expressive enough to actually fit, start fitting noise and get very small training error, even in the case where we have quite large label noise percentage, what happens after this, what we call interpolation threshold? Okay, is if we increase the model size even further. So this is what we call the overparameterized regime. And the question is, how does the test error behave as we increase overparameterization? Training error is kind of clear. The more flexible you are, the easier it is to fit your training error, so it goes down. Test error was not clear, so it could have gone up further as the variance continues to increase. However, what the experiments have shown is that we have a second descent, right? So we have a first descent over here, which is due to decreasing bias, so we get actually expressivity. And the second descent here is something that was curious that researchers found. Okay, so this is the first curious phenomenon, is that we have a second descent. And I will, in the first part of the talk, go through a few calculations where you can see and hopefully get intuition for why this happens. By now, it's kind of well understood. Okay, so that's the first interesting phenomenon in the double descent curve. There's another interesting phenomenon, which needs a bit more time to explain. So here we don't have any training error anymore. All of these lines are the test errors. And they're the test errors of each model architecture or with model with a certain width parameter that is recorded at different epochs, right? So for example, the yellow ones over here are the test errors of the models that are trained only for at most 5 epochs or so. And the further you go, the darker the curves, the longer the networks have been trained. Okay, and so one thing to note here is the red line is for each model width or width parameter, we take basically the epoch with the smallest test error and then record that one, and that's the red line. So it's kind of the optimally early stopping or early stopped network. Okay, so if we compare the dark blue one, which is trained until convergence, and the red dashed one, which is the early stop version, we'll see that for width parameters that are around the interpolation threshold, there is a big benefit in stopping early or regularizing. Whereas in later parts, if we have very large networks that are very heavily overparameterized, it doesn't actually help that much anymore to regularize or to early stop. Okay. So the essence of this slide is to say for very large models, we can actually get reasonably good test accuracy, as good as the best regularized one. So there is no harm in interpolating. Okay, any questions on these empirical observations so far? I don't see. Then let's move on.
Fanny, there is one
question.
Yeah, there is one.
I don't see half of the.
Hey, Fanny, I want to ask you a question. So in this plot, I guess all the hyperparameters are fixed except for the network width. So in the limiting of the right-hand side, will the network enter the NTK regime?
Yes, basically, you can think of it this way. Yes. Yeah.
Does that mean like NTK gets you the best test error?
That's a good question. So the thing is, in the limit, this thing will not continue to just go down. It will at some point go up again. And that's due to the bias problem, actually. So this is only a snapshot, right? So if we go really, really to the very, very large limits, this is not going to only decrease. So this is a little bit misleading in the sense that you think like this is going to continue.
So there are actually not just the double descent, but also multiple descents.
There are multiple descent, yeah, yes. Yeah. Yeah. Good question, yeah. Okay. NTK is also a problem.
Actually, just can you clarify what you just said?
Mm-hmm.
Because it sounded from what you said that there are multiple ascents, not multiple descent. There's the double descent, and then there is an ascent, right?
Yes. There's also papers that are looking at exactly depending on different x-axes. You have multiple descents or ascents. Maybe we can just look at further down in the talk, you will see a little bit what I mean by having an ascent. And that's due to basically the bias that has to increase at some point. If you have literally no information, if you increase the model, at some point the bias will dominate again. But the question is if there is a good phase in between where the bias is not that large yet, and the variance has decreased, and that's kind of the sweet spot. But afterwards, if you go further and further, at some point it's going to ascend again. That's my point. But hopefully it gets clear when I go into a bit of detail. Okay, yeah, thanks for the questions. Okay, so basically these empirical observations were just to motivate or led to quite a few papers motivated by this observation, and these were just some papers that kind of called for action that that the statistical learning community should try to explain this phenomenon. Okay, so yeah, so this paper was uploaded 2016, and then this still was added 21. So basically, we did make some progress, but it's not yet fully understood. Okay. So what did we try to understand, or what did the field set out to understand? So these are the two phenomena that I explained or that I described. And so basically, so this was the underparameterized regime where variance increases, bias decreases. And what was important for the overparameterized regime, that basically the trend is basically opposed, meaning the variance decreases and the bias increases. Okay, and then the question was, when does the variance decay? So when is the point where the variance is sufficiently decayed while the bias is still low? So this is when basically overparameterization and interpolating in the overparameterized regime is benign and doesn't lead to severe overfitting. So the question is, when is this the case? And that's what this talk should give a glance of. Okay, so we started motivating the whole problem with empirical observations on neural networks. Of course, that is hard to analyze. Deep learning theory is, there has been a lot of progress, but not enough yet to give a lot of satisfactory answers. Some problems are, of course, feature learning, understanding that properly, and the effects of depth and width, especially for deeper networks beyond 2 or 3. And then we have non-convex loss, of course, that makes everything hard. So we are not going to focus on understanding this phenomenon in the neural network land, but we are going to linear interpolators. There has also been work on neural networks and kernel learning that I will not touch upon, but you can find them in the references that are on the tutorial website. So basically, we're moving from the width of hidden layers as an overparameterization quantity towards number of features or number of or the ambient dimension for linear interpolators. And the good thing about linear interpolators, of course, we have convex losses that we can understand better, and linear interpolators are just much easier to analyze. And interestingly, we can find similar phenomenon for them as well, so that, and that's the kind of the starting point. If we cannot even understand linear interpolators, then is there hope for neural networks, understanding neural networks? So that's kind of the motivation for why we're now entering linear land. Okay, so now the overparameterization, instead of being width, for example, it's how much larger the dimension is compared to the sample size. And so the larger D compared to N, the more overparameterization I have. Okay, so hopefully I'm motivated linear interpolators. So this talk will comprise of 2 parts. So the first one is about getting some intuition for the second descent with some simple calculations, maybe also for the bias if there is enough time. So we want to understand variance decay. The bias increase is kind of intuitively clear, so we can skip that or do it depending on what people like. And then in the second part, we will focus on how in what kind of situations the bias will stay low. Right? So variance decrease is not enough. We also need the bias to stay low in order to achieve good generalization. And there we'll look at known work, previous works that focused on a fixed interpolator, which is the min L2 norm interpolator, and looked at different distributions of the covariates that lead to benign or non-benign overfitting. And then in the end, I will also present some of our work where we focus on a fixed distributional setting, but where we are changing or looking at different interpolators. Okay, so that's the plan for today. Before we go on, let me just be clear. I'm asked oftentimes in this kind of talk, like, should we use these kind of interpolators? And my answer usually is the whole kind of field of research is not really to find better interpolators to use in practice, but more like adding a perspective or shedding light on when interpolation is not too bad. Okay, when interpolation leads to benign overfitting. Okay, so hopefully that's clear what the agenda is. Okay, so let's start just setting up what interpolating solutions are for regression. So here we have data xi. These are the feature vectors, and yi are the labels. And then we can write them in terms of matrix vector notation that is quite usual and common. And so the interpolating solutions w hat are all of those that satisfy x w hat equal to y. Okay, and now in the overparameterized regime, when D is much larger than N, and typically then X is full rank if it's random design, then we will have infinitely many interpolators, right? We have a subspace D minus N where there are infinitely many interpolators in there. So the generalization performance will crucially depend on which one of those interpolators, of these infinitely many interpolators, we analyze. Okay, so which one are we going to analyze? So the first one is the one that arises very naturally from just running gradient descent on the square laws. So here I will mention two kind of implicit bias notions, or actually three, but two. So the first one is the implicit bias of algorithms. It's essentially a property of an optimization algorithm that is trying to minimizing a loss. That algorithm has an implicit bias towards a certain interpolator. Okay, so the implicit bias of algorithms could help us to pick which interpolators we're going to analyze statistically. Okay, and so a concrete one, as I said, naturally to consider is just running gradient descent on the square laws initialized at 0, and what we arrive at is the minimum L2 norm interpolator. That's a standard exercise that you can figure out yourself that this is true and verify. And so this is basically, among all of the interpolating solutions, the one that has the smallest L2 norm. And one nice feature of this solution is that it has a closed form, so that we can actually use random matrix theory, etc., to analyze it very directly. And that's why also, not that's why, but in the beginning of this field, a lot of focus was put onto these minimum L2 norm interpolators, and a lot of progress was made understanding those. Okay, and that's what we're going to look at in the first half of the talk. Okay, so if we want to analyze...
Oh, Fanny,
sorry, there's a question.
So I can't hear.
Does arriving at that interpolator require initialization at 0?
Yeah. Right. Okay. So now if we want to analyze the performance of like the generalization performance of this interpolator, we need to make some assumptions on the distribution. So not the pack learning kind of style, but we want to know, depending on the distribution, what is the generalization performance. So what do we assume? We assume that the x's are coming from a certain distribution. So each row of the x's are, for example, drawn from a Gaussian. This talk will focus on Gaussians. Just for simplicity, there's also results for sub-Gaussians and just general distributions, but I won't focus on them just for simplicity. But in the reference, you will see more general results. So each row xi is drawn from some Gaussian with the covariance matrix sigma, and the y's, the labels, will be given by the linear function w star transpose x plus some noise that is also normal here for simplicity. Okay, so then we can write y as x w star plus the noise vector. So the degree of overparameterization for linear models, there are two regimes essentially people have looked at. One is the proportional regime where d over n converges to some constant gamma that's bigger 1. So we have overparameterization as n goes to infinity. So that's the proportional regime. And then there's lots of work that analyzes the asymptotic behavior of the generalization performance of the bias and the variance in this regime. And the other regime is when d is of order n to the beta and beta is bigger 1. So it's grows strictly faster than n, and that allows also for the error to vanish. So this is why I call it the consistent regime. And that's, in the beginning, we'll look at the proportional regime, and then we'll look at the consistent regime a bit later, where we will actually consider rates as how fast the error goes to 0 as n goes to infinity. Okay. So first, if we want to analyze the prediction error, we need to decompose it, similar to what we know from textbooks, kind of the bias-variance trade-off. We'll do something similar, but it will be a bit different, perhaps. And we'll see why. So let's think of sigma equal to I if you just want to follow. For now, I will discuss also the other case, but for now, it's just easier if you think of sigma equal to just the identity I. So the prediction error, how do we define this? We want to know the prediction X transpose W hat. How close is it to X transpose W star, the true solution? So we are not looking at the one with the irreducible error plus sigma squared. We just ignore that part. And we want to know what this difference is squared if we average over X from the same distribution that we sampled our training examples from. But they're independent from the training examples. So that's why in the end, you can write this prediction error like this. This is essentially the weighted parameter estimation error averaged over the training data. Okay, so we can decompose this error. And the way I decompose it here is trying to disentangle the effect of noise and the effect of having an undersampling error. So on the left-hand side, this is basically the expected conditional variance. Okay, so conditioned on X, what is the variance? The conditional, that is basically this part over here. And then if you then take the expectation over X, you have the expected conditional variance. So here, this term essentially just captures what the effect is of having to interpolate observational noise, Xi. Then the second term is capturing the effect of undersampling, because we have n smaller than d, and the effect of the particular choice of W hat, the structure of W hat. That is mostly captured in this one. It's also captured in the other term, of course, but this structural effect is larger on this one. Okay, so this is kind of disentangling the two effects. One is due to the noise and one is due to the undersampling. So now I just wanted to go through a very simple calculation where we can see if we look at these two terms for the min-L2 non-interpolator, that we see that the variance decreases. So the variance is this term over here. I just called it the variance, although it's not exactly the total variance. But this term will go down as we increase D, and the bias, which is what I call this term, it will increase. And for simplicity, I will use sigma equal to identity. Okay, so yeah, I'll do the variance, and then you can vote on if you want to also look at the bias. So what's the first, before I go into the calculation, what's the intuition why the variance should decrease as the dimension grows? You can think of, let's think of W star equal to 0, right? So in the end, what you're trying to find is some W that satisfies X W equal to noise. And if you have more dimensions that are available to you to fit this noise, each individual element of this W will be much smaller. So you can think of this noise being able to hide in a lot of dimensions. So if you actually have some W star, this part that is fitting the noise is not going to influence any particular direction too much. So it's kind of spreading out in many directions. And that's why the more dimensions you have, the more you can spread it out, the smaller the effect of the noise will be on the error. That's the intuition. And so here I just want to do a short calculation that shows this. Okay, so we start with, okay, hopefully this fits. So what is, this is the min L2 norm solution, subject to this. Okay, and so we can find this with a very simple calculation that we also sometimes go through in intro classes, but you can basically write this as xxt y. So this is equal to okay. So now this part is the expected W had to condition on X if you take expectation over the noise, and this is W had to minus the conditional. Another thing to note is the second part. So this this part is exactly equal to the part of W hat that is fitting the noise. So this is equal to argmin such that xi equal to x. So it's the minimum norm noise fitting component, basically, intuitively. And now the expected conditional variance, that was, okay, this is the expected conditional variance. That's equal to minus this, oops. Oh, sorry. Yeah. Okay. Okay, so we can write this down because we have this term over here equal to this thing in the norm. So this would be this here. Okay, now it's easy to see that just using the trace trick, not really a trick, but yeah, just the circular property of the trace, then you get that this is equal to trace of t minus 1, given that psi is from normal 0 sigma squared. Okay, now we need to kind of understand how this trace term looks like. How does it depend on n and d? And basically, you can think of X as transpose if X is from 0 identity. You can think of it as a sample covariance matrix where the, so xxt looks like this. Now you can think of that as a sample covariance matrix which has n-dimensional vectors, right, that are also drawn from n0 identity, but now the identity is in n-dimensional space. So you can think of this as a sample covariance matrix which has a Richard distribution. So the inverse has an inverse Richard distribution. So once that's clear, you'd also know that the expectation of XX transpose to the minus 1 of this is equal to this identity over d minus n minus 1. Right, so now the number of samples is d and the dimensions is n. The dimension is n. So we kind of flipped the two. So this is just by definition of inverse Richard. Nothing really happened. And so if we do this, we switch the trace and the expectation. we basically get trace of in, and that's equal to n over d minus n minus 1. So that is just the expectation of the variance, the conditional variance. And you can already see, so if d is much larger than n, if we are in the regime where d grows faster, for example, then this is basically n over d, right? So d dominates n in the denominator, which means that as you increase d, this variance is going to decrease. So this is basically the scaling of the variance, and not just for this particular case of Gaussians with of Gaussians, but it also holds for sub-Gaussians and for also not just only for the Menel-2 norm, but also for Menel-P norm. Okay, this is quite a universal kind of scaling for linear interpolators, for isotropic covariances. Okay, so are there any questions?
Fanny, we have a question.
Hi. The distribution of the target depends on D, right? Because Y is a sum of D variables plus noise. So for different D, it's a different target you're trying to predict. So can you really compare the variance when you're trying to predict different things?
Yeah. So that's a good question. You're saying, okay, so the problem I'm considering is actually changing as I grow the overparameterization. You can think of the setting where, say, the very important features that you want to learn, which is, let's say W star is, for example, sparse, right? If that's sparse, then basically only a few features matter. And you want to know what happens if you get a lot of unnecessary features as well in your data. So say like you measure many more features than you actually need and that are actually relevant for your problem. So then the problem kind of stays the same, but you just have a lot of more measurements that are not necessarily helpful. So that's kind of one way to think about, is it still the same problem as, as we increase overparameterization? You can think of it is the same problem, but you have more and more measurements, and many of them are not really useful. I hope that helps. Yeah, I had the same kind of problem in the beginning, because for neural networks it makes a lot of sense to increase overparameterization. You don't change input-output, right? But what does it mean as to increase the, and so for linear, that's how I think about it. And the sparse structure is also something we will focus on in a few minutes. Okay, so I think in the interest of time, I will not go through the bias.
Fanny, I think I saw a message from Shai pop up, but you can see it maybe and we can't on Zoom.
Yes. Yes, so Shai is saying, it looks to me like this analysis heavily relies on the assumptions on the specific distribution of the X and the noise. That is true. The kind of calculation I did here, they're very simplified. But as I will also point out, for example, spy covariances, the idea is still quite similar. So there, Peter is the expert in this, and others, there the effective rank will play a bigger role. Even though you have a spy covariance, you're still having one part that is essentially isotropic, this essentially has a very heavy tail. And so then a similar kind of reasoning also goes through, and intuition. So that actually doesn't change that much. So you just need a lot of dimensions that are similarly weighted and not too small. And then if you have a lot of those, the variance will decrease. That's still the same idea. So even if you have a spy covariance, that's the reasoning will work. But it's of course much more subtle, and we won't be able to go into this detail. This is just a kind of proof of concept, kind of short calculation to show that why it cannot make sense, that it can make sense to increase D to decrease the variance, increase D to decrease the variance. Okay, thanks for the questions. Right, so yeah, for the interest of time, I will not do the bias calculation. I'm trying to kind of get this Zoom thing back somehow. Okay, now. Okay. Yeah, just wanted to note that intuitively, what we are considering here is this conditional, the conditional expectation of W hat 2 subject to a condition on X. And we want to know how this differs from W star. And the key here is how much of the signal can I still preserve, even though I'm subsampling. And I'm subsampling in particular subspaces. I only have n, but I still need to kind of learn the n-dimensional vector. So the hope is that we're not losing too much of the signal here. So if we use the same assumptions as before, then this conditional expectation is just going to be the projection of W star onto the n-dimensional subspace, which is the row space of X. Okay, so here I'm just writing these sigma hats to be the actual sample covariance X transpose X. And that X transpose X is not full rank, is at most rank n, so we can't invert it, etc. Okay. And so if kind of the intuition why the bias increases as D increases is that that if all subspaces are equally likely to be sampled, so which is the case in the isotropic covariance case, then you can think of these projections onto the n-dimensional subspaces. They're going to also be kind of you will get, for each X, you'll get a random n-dimensional subspace, and you'll cover these different possible n-dimensional subspaces in a similar way. So on average, you can retain n over D fraction of the original signal. So I won't go through the calculations, also relatively simple. But so in the end, what you get is that this conditional, the expected conditional bias is going to be so D minus N over D. So N over D is what you can retain. And that is 1 minus N over D is the missing fraction of the original signal. Okay, so here's actually, if you're interested, there's a nice argument that you can find in Ryan and Ryan's paper and Trevor and Andrea and yeah. From 2019. So there you can find this very simple argument to check why this is D minus N over D. Okay. Just in summary, what have we learned? So first is, as we increase overparameterization, variance can decay, and hence this leads to the second descent, which is this one, second after, so this is interpolation point. So after interpolation, we have a descent. On the other hand, for isotropic covariances, the bias is an issue. The bias will increase, and it's not only for isotropic covariances, but for isotropic covariances, we have the bias being actually quite large. As D increases, it will converge to essentially the signal itself, the signal strength itself. And that's also maybe what Samori was asking earlier with the ascents. So you can see there is going to be an ascent at some point, because the more flexibility you have, the bias will always increase. It's just how fast is it increasing? That is the key question. And if it's not increasing too fast, you'll have a nice plateau where there's some good trade-off between the bias variance. But if it increases very fast, like in this case, then you'll see the increase very, very early. Okay. So what you also see, if you look at this formula, is that we don't have a vanishing prediction error as N and D go to infinity, no matter how you're going to choose the regimes of N and D. Also for large D, we'll have a large prediction error, which is due to the bias. So even though we understand second descent, we still do not understand yet when interpreters can achieve good generalization. And this is what we want to look at in the rest of the talk. Okay, so any questions on this? Not, then I'll continue. So the question is, which factors are governing whether we get a good bias variance trade-off where the bias doesn't increase too fast, or a picture like this where the bias increases so fast that we don't really have a good large model. Like we cannot find a large model with good generalization. Oops. Okay, and the two factors that I want to discuss are the covariate distribution if we have a fixed interpolator, and the structure of the interpolator when we have a fixed distribution. So let's start with the first one, which is what has been studied before our work quite a bit by people in Berkeley, such as Peter's group, and others. So let's fix the min-L2 norm interpolator again. And now the question is, how do we get from this picture where the bias increases fast to this picture where the bias increases slowly? Okay, so here's just some experiment that shows what helps. So this is the experiment for isotropic covariances, but if we now change the covariance to a spiked one, which means that we have, let's say, small k number of components that have very high eigenvalues and a lot of components with small eigenvalues, but they are, let's say, it's really a step function. Then if we run the experiments, you will see that the bias is going to be much smaller than in the isotropic case. This is the prediction bias. Okay. So in total, we will get a smaller prediction error if we use this spike covariance. And now, why is this the case? I will only give a short intuition because we don't really have a lot of time. So as we increase the spikiness, that's in this case, the ratio between lambda h and lambda l to the extreme, if you consider the extreme, what happens is that this, the bias, the expected bias that is this here, this expression, the error vector, which is this vector over here, is essentially d minus k, it becomes a d minus k dimensional projection into the directions that are not heavily represented in the covariance, right? Because this sigma hat transpose or pseudo inverse sigma hat is going to lie in the k directions of the sigma, and or just k first directions in our case. And so if you project onto the complement, that's going to be all the other directions. And any error that is in all the other directions any error doesn't matter in those directions, because in the prediction bias, or the prediction error, you will weight this vector, which is lying in this subspace d minus k dimension subspace. It'll be weighted by the sigma, which focuses on the k dimensions, right? And in those dimensions, you don't have a large error. So in the end, your bias is going to be much smaller. That's why kind of for the bias, having a spike covariance is a good thing. There are some caveats, of course, which is in the overparameterized regime, you also want the variance to decay. And if you choose a very spike covariance, which is just, in the extreme, all the lambda L's are 0, and you have a lambda k with k much smaller than n and d, then you essentially have a low dimensional problem. And you have the problem of the variance is that it's going to be a very large. So instead of n over d, you have essentially n over k. Okay, so you'll have much fewer directions where you can absorb this variance if you're still forced to fit the noise. And then this also means that your variance will grow way too much. And so you have to carefully do this trade-off and find a spikiness that gets good rates and consistency. And if you are interested, Peter has 2 papers that are very, very nicely deal with this case and analyze this trade-off using the concept of effective ranks. Okay. So this is the story for a fixed interpolator. So one factor that can govern whether overfitting is benign or not is the covariate distribution, or more clearly the spikiness of the covariance. Another question is the opposite. Now, if we're stuck with a certain kind of data set or certain distribution, in this case an isotropic one, can we also find a good interpolator, perhaps using different optimization algorithm, that actually also leads to a decrease in the bias? And that is the last 20 minutes will be about this question. And that's based on joint work with my students, Konstantin, Guillaume, Stefan, and Nicolo. Okay, so I mentioned in the beginning, there will be different notions of bias in the talk. So the first notion was the implicit bias of the optimization algorithm towards a certain interpolator. And so we looked at the particular optimization algorithm being gradient descent initialized at 0. It converges to the min L2 norm interpolator. But there are many other possibilities other than gradient descent. There's other first order methods, mirror descent, coordinate descent. And depending on which one you use, you'll get a different interpolator. In particular, you can, there's been work for P not equal to 2, for P equal to 1. And very early work by Efron et al. Showed that you converge to the L1, a min L1 norm interpolator, if you run essentially a coordinate descent type algorithm. And so this kind of motivated us to look at interpolators where P is in between 1 and 2. And here, that's where the term inductive bias comes in, also mentioned by Nati before. It's kind of, so the optimization algorithm has an implicit bias towards an interpolator. The interpolator that you get then has an inductive bias towards a certain structure. So this is kind of how we kind of think of these different biases. So one is a property of an optimization algorithm, and one is a property of a particular solution. And the inductive bias has to do with basically structure. For example, this could be sparsity or certain invariances. And depending on which interpolator you have, you will have more of a certain kind of structure. Okay, so we will focus on the effect of the inductive bias of the interpolator, how much there is inductive bias towards sparsity, and see how this affects our generalization. Okay, so first I just want to recall the standard statistical theory on linear sparse or sparse linear regression, where it's kind of clear that if you choose P close to 1 or P equal to 1, you have a very good inductive bias for your estimator. So the first one, so first the distribution we consider same as before, linear model with noise, IID noise, but now we also assume that W star is sparse, so it only has k non-zero entries. So now what is the picture for first for the noiseless case if we want to interpolate? So assume xi is equal to 0, so there's no noise. And W star is sparse in this illustration. That's just a 0, 1. And if you now look at all possible interpolators, they will lie in some subspace. Right. So this is just an illustration here, and depending on whether you choose P equal to 1 or 2, you'll get different solutions. Right. So for example, if you choose P equal to 1, which means you're looking at the min L1 norm solution, you will find because of the geometry of the L1 ball, you will find a solution that is rather sparse. And that aligns with the W star structure, which is sparse. And so we say the L1 norm has a strong inductive bias towards sparse solutions. Right? And in contrast, if you choose a P equal to 2, then you're not really restricting your search space in the right way, meaning you are not using the prior knowledge that W star is sparse. And then you'll find some solution that is on the subspace of interpolators, but far away from W star. So you have a weak inductive bias towards sparse solutions. Okay, so this is all, most of you will know all of this. So if you have a noiseless data, the min-L1 norm interpolator is actually optimal. So you won't get better if you use the non-convex version, which is minimizing just the number of non-zeros subject to the interpolation constraint. And you achieve perfect recovery with high probability, only with roughly k number of samples. Then the key was, if you now allow for xi to be a non-zero, so you have noisy observations, then what is also well known is you can just penalize the square norm with the L1 norm, and you can achieve minimax optimal rates with the lasso if you choose the good lambda, the penalty coefficient. Okay, but what's happening here is, so the second case, once you have noise observations, what you're doing with this penalty is that you're saying, okay, I'm trading off data fit with structure, right? So basically, if I increase lambda, then I care less and less about the data fit, which means I'm really like actively not interpolating for the sake of having a small L1 norm. So what has not been answered is exactly this question is, what if I actually use basis pursuit, which is the same as the min-L1 norm interpolator, to fit noisy data now, right? So when I don't have noiseless data, how good is the rate going to be? Right? Is that still optimal to choose p equal to 1? And all these questions were not known before. Okay, so what is happening in this case, in the same picture? So now the noise is not 0, which means that the subspace of all interpolators is not going through W star. So W star is not a solution of the interpolation, because it's not feasible, basically, of this constraint when we have noise. So now we can do the same. We look at the minimum L1 norm solution. It's going to be on this 0x axis. And this will look like this in our illustration. And even in this 2D illustration, you can already see the following. Okay, so min L2 norm is also going to be far, but you can see that maybe there's something in between, some other LP norm in between that will get you a solution on the subspace of interpolators that is closer to W star than both L1 and L2. Okay, so we are varying our inductive bias between the strongest one and the weakest one, and maybe there's a benefit to choose something in between. So that's already something that you can see in this kind of cartoon illustration. Okay, so what we're going to focus on is the strength of the inductive bias, which is the same as choosing p in between 1 and 2. How does that affect the generalization performance? Okay, and the overparameterization regime we are looking at is this, where d is of the order n to the beta, with beta bigger 1. So we actually can achieve vanishing error. So we are in the consistent regime, not in the proportional regime. And the larger beta is the more overparameterization we have. And yeah, we are focusing on the isotropic case, where, and also we don't look at the expected error, but we look at, with high probability, how large is this error. So it's a slightly different than the calculations I did before. And so we want to know this error, how does it decrease as a function of n and d? And so this is captured by this function that I call h. So it's basically going to be a function of n and d that we're trying to find. And also, interestingly, our results will be tight, meaning that there's lower and upper bounds for this error that are of the same order, same dependence on n and d. Okay, so we want to know how this h looks like. And for different p's from 2 to 1. And we'll start, well, we already know for p equal to 2, you do not get consistency. So the rate is basically of the order 1. And so what happens when we choose p equal to 1? Well, p equal to 1 has the advantage that it decreases the statistical bias, because it helps us to search in this high-dimensional space only in the directions where it's more likely to find the ground truth, which is a sparse one. So we're searching only in the space of sparse solutions, essentially intuitively speaking. So expect maybe there's a benefit. Okay, so how large is the benefit? Can we still get consistency? So people have looked at this in different contexts. So there were some bounds for adversarial noise vectors where the xi's are not IID. So this is a harder case. There, they also got only a constant error bound. And it wasn't clear if you have IID, you get actually something that's a non-constant and can actually decrease. There was a lower bound that was saying, okay, maybe you can get to 1 over log d over n, which would be consistent, right? If d is n to the beta, then you get 1 over log n. And yeah, so in our work in 22, we actually showed that this is exactly the tight or the correct bound, which is that indeed this is achievable by the L1 min L1 norm interpolator, and that you get the rate of 1 over log n for p equal to 1. Okay, so what does that mean? You know, I mentioned this in the very beginning that for neural networks, it was the case that whether you regularize or not, which means if you sacrifice data fit or not, didn't really make a difference for large models. But if you look at this rate, 1 over log n, it is far from the regularized rate, right? So it's a lasso rate, which is of the order 1 over n or k over n. So basically p equal to 1, even though it's better than p equal to 2, it's not really matching what is best possible. And so the question is, can we do even better than this? So we're not happy with this yet. So what is the problem with p equal to 1? The problem really is that so here we see actually okay, so maybe here it's clear. So we see that the variance of p equal to 1 is actually what is the problem. So as you go from p equal to 2 to 1, so in this direction, the variance is increasing. So even though the bias, which is this gray line here, this I don't know, dash dotted line, even though the bias is decreasing, the variance is increasing. So you can also think of maybe as a high-level takeaway, right? So in this case, usually you would say, okay, if you have less flexibility, then the variance should decrease, right? So you're shrinking the function space that you're searching over. And here, because we're forced to interpolate noise, the sensitivity to noise actually is increasing if you have less flexibility, right? So basically you have to use very few dimensions or very few directions to fit the noise if you're limiting yourself to sparse directions, which means that your variance is actually going to be larger if you have smaller flexibility. Like p equal to 2 has more flexibility because you can basically spread it in all directions. P equal to 1 doesn't allow you to spread in all directions, but only sparse directions. Okay, so here we have the opposite problem. So the bias is good, but the variance is large. So then the question is obvious, right? So if p equal to 1 has a variance problem, p equal to 2 has a bias problem, is there something in between that can trade off those in a nice way to get a good rate? And how fast can this rate be? And so this is the question here, which rates are in between p equal to 1 and 2? And so, yeah, in the last, I guess 6, do I have, or 10 minutes? Do I have 10 minutes?
Yeah, you can take 10 minutes.
Okay. Yeah, last 10 minutes, I'll just go through these results quickly. Okay, so we're still in the regime where d is of the order n to the beta. So on the x-axis, you see this beta. And then on the y-axis, you see the exponent of the bound. So we plot alpha on the y-axis, where alpha is essentially the exponent with how fast it goes to 0. So if alpha is negative, otherwise it wouldn't go to 0. And so so the larger the absolute value of alpha, or the closer it is to -1, the closer it is to optimal. Maybe I should go here. The minimax optimal rate is alpha equal to -1, which you can achieve if you use the lasso, but that's a regularized solution. Then interpret this with p equal to 1 or 2. So here I only plot theta tilde, which means I'm ignoring log factors. So 1 over log n is essentially like 1. So interpreters for p equal to 1 and 2 have alpha equal to 0. It's essentially constant. And for p in between 1 and 2, you can actually get alpha to be negative, strictly negative. So you have a polynomial decay. And this polynomial, this exponent, will depend very much on your p and your beta. I will not go into detail here. It's quite involved. But what you can see in this picture, that you can at least populate and achieve these rates of close to the rate of 1 over n. If you choose p that is relatively close to 1 and beta larger than 2. Because that's basically the takeaway of this plot. We plotted basically the exponents for fixed beta, for fixed p, and varied the beta. In order to do the other plot, there were some caveats in analysis that didn't allow us to do that, but I didn't want to go into detail on this here. This is just to get a sense that it's possible to actually get very close to 1 over n, to the 1 over n rate, if you have a lot of overparameterization due to the variance, right? You need large enough models. And a good bias because you're close to 1. And yeah, so the variance, beta helps with the variance, but also a larger p helps with the variance. So just choosing p a little bit larger than 1 allows the variance to be small enough such that you get this polynomial decay instead of 1 over log n. Okay. Okay. So this is the takeaway. This is the full picture. P equal to 2 and p equal to 1 have problems. In one case, it's the bias. In one case, it's the variance. And you can get a good trade-off in between for p in between 1 and 2 to get polynomial rates. And another takeaway, a little bit higher level, is that what kind of interpolators work well when you have noisy data? It is when you use not the interpolator with the strongest inductive bias, but with a medium strength of inductive bias. Okay, so this also allows you to translate this kind of intuition or insights that we got for linear models to neural networks, for example, so images or else. So I won't go into detail. We also have some work on this one paper where we looked at invariances, for example, rotational invariance, or filter sizes as an inductive bias, and where we kind of show that if you have noise, you don't want to constrain your function too much during training. And if you don't have noise, that's the best thing to do. So that's something that is a takeaway that might go beyond just linear models. Okay, okay, a couple of minutes I still have. So yeah, so I just talked about regression so far. How about classification? The proof technique that we used in the previous papers for Gaussians also allowed us to immediately go to classification using localized uniform convergence, also by Nati's group, and the convex Gaussian min-max theorem that allowed us to prove essentially the same things as for regression. So that's why I don't spend that much time talking about it. If you run the experiments, you can see exactly the same story, also experimentally. So maybe just focus on the right-hand side, where we have a real-world data set, the leukemia data set with large dimensionality and few samples. And now sigma is the amount of noise that's in the data, or like added noise. Right? And so the blue line is for the case where we don't add any noise. And the other ones, for the other ones, we added a little bit of artificial noise. And here you can see that if you fit a linear model using the cross entropy loss, whatever, then if you choose P to be to be 1, it's the best for the noiseless case. But if you have a little bit more noise, then you would like to choose P as a bit larger than 1 to get the best test error. And then you can see the kind of same story for classification, even in those simple experiments. Okay, that's beyond regression. There's results in classification. Then beyond linearity, we have some results for kernel learning, where the inductive bias is the filter size for convolutional kernels. We then have the experiments for neural networks that suggest this similar behavior for rotational variance and filter size. But it's not the end of the story yet. So these are just preliminary experiments. And then lastly, we also extended our results beyond Gaussians and also beyond just kernel or linear kind of function spaces to more general and nonlinear function spaces based on a function analytic approach and framework. It's still work in progress, but can already find the first results in this ICML paper. Okay, so that's it from my side. If you want to know more about benign overfitting, it's worth checking out our tutorial website. And then these are the papers for the second half, where it was about the structure of the interpolators, if you're interested. Yeah, so thanks a lot for your attention.
Thanks, Fanny. Do we have more questions for Fanny?
Thanks. I think I find the L1 LP interpolator result very interesting. So I want to ask actually 2 questions regarding that. First, you said something like the optimal P norm interpolator you should choose. It's some P very close to 1, but when P actually goes to 1, the rate suddenly decrease from polynomial to 1 over log n. So why there is such a sharp transition? If you can share some insights, that would be grateful. And second, it's like for Lasso, the rate is linear in K. K is a sparsity level. So how does the sparsity level enters your interpolator bounds? That's the second question.
Yeah, the second question. So basically, in our case, the noise fitting is dominating. So there, basically, is as long as n is larger, the sparsity is not as large as n, then you can get these results that don't depend on the sparsity directly, because basically you're sparse enough such that your bias is fine, and then everything is dominated by the variance, so it doesn't appear concretely there. It's basically just viewed as a constant there. For the first question, what was the question again? That was regarding the P sharp transition. Yeah, that is quite puzzling. You can think of so basically the L1 ball is you can think of it as kind of it's perfectly unsmooth. So once you add a little bit of smoothness, there is basically a phase transition in what you can show. So also, if you want to know more in this last paper on uniform convexity, maybe you can get more intuition why this is the case. For our case, we actually don't have something in between p equal to 1 and 1 plus 1 over log d, essentially. And that has to just do with the concentration of LQ norms of Gaussians in our analysis. But I think the other paper makes it a bit clear you need like some sort of uniform convexity of your geometry of the norm balls has to allow that for the variance not to blow up. So that's all I can say. It's a bit hard to kind of really pinpoint the intuition clearly, but yeah, good questions.
Yeah, I also had a question about like, so you focused on like I guess the part where like you fix an interpolating classifier or interpolating predictor, and then you have like a specific p norm. But I was wondering like what, and it might just be because like I don't really know the literature, but like what first order methods or algorithms give those like like p equals 1.1 or something like that? Like, is it like just like mirror descent with the specific regularizer or something, or
yeah. So as far as I understood the results from Atyadal, but maybe he can correct. So these results that show that basically you converge to this min LP norm, this holds only for strongly convex. Okay, now this is kind of far. For strongly convex norms, so for p larger than 2. So in between 1 and 2, I'm not aware of a specific implicit bias result, but maybe the experts, there are some experts in the room that are aware of that. Yeah, so for us, it was primarily statistically interesting to look at the p in between 1 and 2 after seeing that there you have this bias and variance issue on both ends. So yeah.
I think Nadia was going to make a comment.
Yeah.
I mean, Matusz wants me to make a comment. There's no, I mean, if you do steepest descent with respect to the LP norm, you maybe sort of kind of get something resembling the min LP norm, but it's not exactly a min LP norm. I mean, it might have the same generalization properties, but it's not obvious. For the squared norm, which is what's studied here, I don't know if any optimization method that's guaranteed to get you exactly the min LP norm. But that's true also. Well, okay, I guess for L, that's true also for L1. So that's not, I mean, there's no optimization method, natural optimization method, as far as I know, that is always guaranteed you to get min L1 for squaredless either. I mean, unless I'm missing something and somebody can correct me on that.
Any other questions? If not, thanks a lot, Fanny, and we hope to see you over here soon.
Thanks a lot, everybody.
Coffee break for about 15 minutes.